What if you threw something perfectly straight up and it didn't come back down in the same place? What if Earth's rotation secretly pushed it sideways while it was in the air, even if you felt nothing at all? Let's break down this mind-bending idea.
Hey everyone, welcome to MindBlown Science, your place for exploring the biggest ideas in physics, from space-time to orbital mechanics. If you love learning how the universe really works, hit that subscribe button so you never miss our deep dives. Why would a vertical throw land somewhere else? Earth is spinning. At the equator, you're moving eastward at about 465 meters per second, over 1,000 miles per hour, without noticing. When you throw an object straight up, it keeps this eastward speed due to conservation of angular momentum. But as it rises, it moves farther from Earth's axis. To stay above the exact same spot, it would need a slightly faster eastward speed than you gave it. Since it doesn't have that extra speed, it drifts slightly to the west relative to your original position. This drift is caused by the Coriolis effect, the same phenomenon that influences hurricanes and long-range artillery.
How big is the effect with real numbers? Here are some clean, real physics predictions. If an object rises 10 meters, like a normal throw, drift is about 1 to 3 millimeters, totally undetectable to you, overwhelmed by small air currents. If it rises 100 meters, like a high drone ascent, drift is a few centimeters, still smaller than wind effects. If it rises 1,000 meters, 1 kilometer, drift is about 10 to 20 centimeters, now measurable if there's no air resistance. If dropped from 3,000 meters, drift is up to about 1 meter, still much smaller than wind, but finally visible in ideal physics world. At rocket altitudes, 10 to 100 kilometers, drift can reach hundreds of meters. Real rockets must correct for this to land precisely. Real world versus physics world. In the real world, air resistance dominates, wind dominates, human throw imperfections dominate. So a tossed baseball, basketball, or stone will seem to fall back exactly where you are standing. In pure physics, vacuum plus no wind, any upward motion results in a sideways drift. The drift grows with altitude and time. The effect is small, but absolutely real and measurable. This is why aerospace engineers must include Earth's rotation in landing predictions for capsules and rockets.
Final takeaway. Earth's rotation does cause objects thrown straight up to land slightly off from where they started, but at everyday heights, millimeters to centimeters. At high altitudes, centimeters to meters. For rockets, hundreds of meters or more. So next time you toss a ball, remember, you catch it only because Earth's rotational effects are tiny at human scales. Stay curious and keep your mind blown.